right, so this is our test for divergence. It's a nice little trick, and what it basically says is if we take our sequence of terms, that's the inner part here, not the series, right? So we're taking just that little sequence, that little inner part, that k squared over here. If we can show that that does not equal 0 or does not exist, then we say that the series is divergent. And it comes from this. If a series is convergent, then its limit is equal to 0. So it's convergent, limit 0. It doesn't work the other way because it's not an if and only if. It's saying that this is 0 if the series is convergent. So we can't say that the limit is equal to 0, then it's convergent. It doesn't work that way. It has to be convergent, our limit 0. So like a harmonic series is divergent, but its limit of its sequence, that inner part right there, is 0. So we're using it in reverse here. We're saying, well, it's not equal to 0, then it's divergent. So if we can show that that inside, that limit, as k approaches infinity, of k squared over k squared minus 2k plus 5, if we can show that it does not equal 0, we show it's divergent. So we already know it's divergent because of what it is. So now you've done rational expressions like this. And we always take the bottom one and we divide by it. So this would be k squared over k squared. K squared over k squared. 2k over k squared plus 5 over k squared. And so we know that this goes to 0. Come on, red. 0 and 0. It's our basic rule. So we end up with the limit as k approaches infinity of 1 over 1, which is 1. And this is not 0. So by the divergence test, this is divergent. So all you have to do is show that it does not equal 0 or that it does not exist, and we get it divergent. So how about arctan then? Well, the limit as k approaches infinity of arctangent, and this is just n, and it wouldn't be k this time, it would be n because it's n. Well, we know that that's pi over 2 as n goes to infinity, which again is not 0, so this is divergent. So that's all we're doing here. We're showing that it's not equal to 0 or does not equal exist, the sequence, limit of the sequence itself. All right, how about this one? So it's not as easy on this one, but you can look, they both have n. That's geometric style, right? So what we can do is what we've done before. If we can show that something that is smaller than it diverges, then the one above it would also have to diverge. So we know 1 plus 4n over e to the n is greater than 4n e to the n, which is 4 over e to the n. And so we just made it into a geometric. So if we can show that this diverges, then of course something bigger than it's going to diverge. That's that rule we've had for a while now. So we now know the limit as n approaches infinity of 4 over e to the n is going to go off to infinity. So this is divergent. We could have also used our geometric, our r here, which is 4 over e. Remember e? E is 2.718. It's going to be less than 4, which means this would be greater than 1. Since our r is greater than 1, it's also divergent. But no matter what, if you find something smaller than it, and it diverges, then the bigger thing also diverges. So if you're looking for divergent, again, make the greater than. If you're looking for convergent, make the less than. But we're doing divergent here. It's for divergent test. So again, that went off to infinity, so it does not exist. It's not 1. And there you go.